we'll start from the beginning. I will write the problem. Remember, I will ask you very specifically to do things like that in your final, as I said. So here is an example of transmission lines. And what I will do is to give you something that has 3 sections of line, like in one of your homeworks. So you have 3 types of transmission lines, but they all have the same characteristic impedance. Well, 2 of them have the same characteristic impedance, the other one doesn't. So one is like this. Oops, that's a little too thick. This one here. All right, so this. One section. Then there is another one. There. And then there is a third one. All right. Now, why I have this in between, you will see, but there are 3 lines that are connected practically. So here, I can show that connection like this. Here, connection, there. All right. At the end, we have a load. And it's a complex impedance. All right, so here, or complex admittance, I will give you an admittance in admittance form. And let's assume that this is 0.02 minus J 0.01. And these are in 1/ohm. All right, and then here I have a source, and it's an ideal source. This source is here. All right, ideal. And there are 2 things. V naught is 1 volt. And we know that P for the source, the real part that the source can provide, is 0.5 milliwatts. That's what the maker told us. So now what I will do, as always, put here, I will start lettering or numbering whatever the line. So A, the ports. A prime is the input port of this line. So this is line number 1, if you like. So we know what we're talking about. Line number 2. This is 2. And line number 3. And then here you have BB prime, CC prime, and then D prime. And as I said, the characteristic impedance of this line 1 is Z naught, of this one is Z naught, of this one is Z1. And now what I'm asking you, I'm giving you rather that this length of D1, of 1 is D1, this length of 2 is D2, D2, and this one is D3. Okay. Now, I'm asking you to do the following. I'm asking you to find, so I'm giving you, let me tell you what I'm giving. So what is given? It's given that what the load normalized, I gave it to you, is 0.02 minus j point, and in fact, it's not normalized. I'm sorry, the numbers that I gave is not for a normalized, plus 0.0101 minus 1. I give you the d1 is, say, 0.1 lambda. I give you that z naught is 50 ohms, or in that case, y naught will be 1 over 50, which is going to be 0.02, I think. Yeah. And what else did I give you? I gave you that V naught is 1 volt. And I gave you that P0 is 0.5 milliwatts. Milliwatts. All right. And then find D2, D3, and Z1. All right. So again, D2, D3, and Z1, so that you have a perfect match, so that you have a perfect match at the source. All right. Okay. Now, this is everything here. We have, you remember what I said, you have to outline your solution. You should not start doing anything without outlining solution. So solution here, and then outline. That's how you think how to solve the problem. All right, so here is how I'm thinking about this problem. I say, well, I have a load which obviously is not matched. Is an admittance which has a real and imaginary part, definitely is not matched, no matter what the values are. And this is on a line, Z0, and then there is another line with Z1. I don't know D3, I don't know D2, I don't know Z1. The only thing that I know is that I have to eliminate all reflections from here. So I have practically, if this is my reflection here at this point, to provide a perfect match. So all of the power that comes from this ideal source is absorbed and eventually goes to the load. So here is what I'm thinking, and I will write it so you see it. For a perfect match, which means all of the source power becomes absorbed by the load. What do I have to do? Number one, I have to make sure that this reflection coefficient at BB prime becomes 0. All right? Which means whatever power from the ideal source enters this transmission line, whatever power from the source comes here, like this, all of it is not, nothing is going to be reflected at BB prime, and it's going to continue. Since nothing is reflected at BB prime, then it's going to go somewhere to the rest of the line. For all of it to go and be absorbed by the load, that implies that, second, conclusion, my matching network, whatever I decide to add, in other words, which I don't know what it is. So the matching network should not include any resistors. So this is important to remember, because if your matching network includes resistors, that implies that whatever power goes into this line, whatever power comes here, part of this is going to be dissipated in whatever I add, if it's a resistive component, and then only part of it is going to go to the load. And I don't want that. I want all of this to go to the load at the end. All of this, I want all of this power, P max, that comes from the source, to go here. So whatever I do, if I add, it has to be only reactive. Then another bullet, 3. I'm observing here and I see, okay, what do I know I can do? Since in this line, I don't know the length, then I can design that length. So I can design it. So at this point in the line, right here, this input admittance, input at C prime, is real. So, and then follow my thought. If this is real, then I can design, so I can find this to be real. If this is real, then I can design D2 and Z1 so that the input admittance here, to see I want to finish my thought here before I write, then the input admittance here, I can make it to be Y naught. And that I can do by using a quarter wavelength transformer. Like without, like practically I can make it 1 normalized. All right, so these are the things that I will I'll leave it a little bit of space to see. All right, so this, and I write it here. So what I can do is then I can define D3 so that in normalized admittance, input admittance at CC prime is real. And then, could you please mute yourself? I can hear some noise. And then define D2, define D2 and Z1 so that Y normalized input at B prime is 1. And then that implies that I have been able to develop a matching. And then if I do that, if I do this, then I have achieved a matching, which means then achieved matching at BB prime. All right, now that I wrote that, I would like to ask before we continue to do these steps. Tell me if anybody has a question, because it's important before you even, as we outline the solution, is important to make sure that you understand why I made those choices. Any questions?
Professor,
Yes,
is is this the only way you could solve this problem?
no. In design problems, there are multiple solutions. All right. This is the easiest for me, rather. But in design, you have to remember, in design, it's like you design a house. Is there only one way to design it? No. That's why we have so many different homes around, different architectures. There are different designs. Now, an experienced designer, of course, for our class, whatever solution you give me, which is a correct solution, is good for me. However, in real applications, when you design for a circuit, there are other considerations that they will drive a designer in selecting one of these possible solutions. All right? There are other considerations.
Okay.
And okay, but for us here, no, but obviously more than one. But this is the, and then I will, as soon as I finish that, I will tell you what other possibilities you have.
Okay. And
Oh,
our matching network is the lines between B and C, right?
the matching network is everything that goes between B and D.
Oh, okay, okay.
All right, is everything that is in between the source and the load is called the matching network.
Okay.
Yeah. Any other questions?
Would you not want YNCC prime to also have a reflection coefficient equal to 0?
If you can, but look at, there is a z. Yeah, if, since I told you, in that case, if you want to make y input, if you want to make the reflection coefficient as CC prime 0, that means that from that point on, I will make Z1 equal to Z naught.
Mm-hmm.
All right, because if you do all of your matching after CC prime, then I don't want Z1 to select a value that is going to create an additional reflection at BB prime. So in that case, if I by CC prime, I have already made my reflection coefficient 0, I will make Z1 equal Z naught. Do you understand that? Why?
Mm-hmm.
Um,
Okay.
that's another possible solution.
And then for Y and BB prime normalized, how did you get 1? What did you divide by?
By Y naught. Y naught is 1 over Z naught. So when you normalize, or if they are impedances, you normalize with Z naught. If you have the load in admittance form, you normalize by Y naught. So for example, here, you can see on the Smith chart, I can go to Z's if I want, instead of Y's.
But were we given YN at BB prime, or how did you solve for that? Like before normalizing it?
How would I select that part of the design? All right, how to make it Y input at BB prime before normalizing equal to Y naught. If,
Okay.
if I make Y input at BB prime before normalization to Y naught, that means that Z input at BB prime becomes equal to Z naught.
Mm-hmm.
And that
Okay.
is going to make the reflection coefficient 0.
Got it.
Okay,
Thank you.
sure. Any other questions? Okay, so now let's try to solve. I'm gonna go and find a Smith chart, first of all. Is that the right one? No. There is somewhere here. Okay, this one, copy. And then, where? Yeah, there. Okay, and then I put it here, paste, and then I will clean it up from previous problems. So then, wait for it. Give me a minute to do that. Okay. Now, number one, what do you do first? We go and find the load on the Smith chart. Our load here is given in YL. So our load here is this one. And then, so if I am to put it on the Smith chart, assuming that I don't have a calculator other for like adding and subtracting, that I cannot do anything else. So I'm gonna work only with the Smith chart at this point. Then I will take this, and since it's not normalized, I will try to normalize it with Y naught. So if I copy it and go here, paste. So let's try to normalize it. What is Y naught? Y naught is 0.02, which means that YL normalized, and in fact, maybe I can put it here, is going to be 1 minus J 0.5. All right, and then I will highlight it so you can see it. Now, what am I going to do? I'm going to go to the Smith chart and try to find it. The same numbers, however, you need to remember that the Smith chart is agnostic to whether you have impedances or admittances. What makes what I have the load and impedance or admittance is how I treat it, as you will see. But for now, I will go and just read the numbers as if it were an impedance. So I will use one. I need to find one. What circle goes through one? This one. Let me show you this and this. So the circle that goes through one, and then I will erase it, is this. All right. And then I have minus 0.5. All the minus are below. So I need now to use a different color and find 0.5 is here. So the circle that gives me minus 0.5 is this one. So practically I have to go and find the intersection of the two. And in fact, I have to do this, the intersection of the two. And that intersection here is going to be YL. And in fact, I will show it to you to write it also. So we have it on the YL normalized. And then now that I found it, I will erase the other two circles because I would like to have it clean. So I will erase them. You will have it on the video to see them though. Now from there, what did I say I'm gonna do? I will define D3. Let's read what I wrote. I will define this number, this length. So when I move from here is where I am right now. That's where my YL is, here. When I move from there towards the generator, this is how I'm moving. I have to stop at CC prime here. And at that point, I have to stop until my input admittance at CC prime is real, or my input impedance at CC prime is real. Either of the two, all right? If one is real, then the other is going to be real because one is the inverse of the other. Okay, that's what I need to remember. So I'm going here now. Question to you. Do you want to work with admittances or impedances? What makes you more comfortable? Or it does not matter? Any preference?
Doesn't matter.
For
Okay.
me, it's impedance. I kind of just feel like I can work better with that.
Okay. So if you want to work with impedances, you have then to transfer the admittance into an impedance, which means that I will find the circle of the transmission line number 3 and the circle of the transmission line, okay, there is going to be this one, whatever has its center at the center of the Smith chart and goes through this point, the point of my admittance, there. And from the admittance, I have to draw the diameter that goes of the circle that will go like this. And at that whatever point I find there, I will use a red one, a red, that's my impedance. So this one here, for you to know, that's ZL normalized. And that's ZL and what did we say? The load normalized. Okay, you see? The moment you do that, then I suggest get rid of YL because then I don't want you to get confused. It's easy. The worst thing you can do is to keep all of the admittances on the line after you have decided to work with impedances. So now you remove it. You remove the YL. Okay, good enough. Do you remember what I said? We have to move on the Smith chart by a distance that is going to make ZL equal to real, rather. Okay, we are going to move until we make ZL real. Where are the points where they have only real value? On this green circle. Which are the points that have only real value? How many they are and which are they?
There's 2 and they're the ones along the horizontal axis.
Yes, exactly. So here, one is here, the other is there. Now, what makes your choice? Which one are you going to choose? Now, it depends on how long of a line you want to have for D3, how long of a D3 you want to have. You only know that you can move along this direction. This is the only direction to move away from your load. You remember why? Because you are moving along this direction. You are at the load and you are moving towards the generator. So the only way to go to do that is by moving along this direction, the purple one that I have indicated. So from where you are ZL, if you move like that, the first point you're going to find is the one with the larger impedance, which is fine, all right? But if you want to find the one with the lower impedance, there is no reason to choose one or the other. The only difference is that you're going to pay a penalty of increasing the length of your line. And usually increasing the length of the line, you don't do unless the distance between the red and the first purple on the right was so short that it was meaningless. So then you would have to move. But now, how I'm going to move, I'll show you here with these arrows that I'm doing. So you know, I'm moving from here on this line until I find that point. This point there, and I will write it here, is nothing else but my ZL. This is point ZL, no, not ZL, Z in at CC prime. This is, and I can put it here. This is Z in normalized at CC prime. See, you can use impedances or admittances. So, and this is real. So I'm going there and I have that at CC prime. Okay. And how much is that? I will write it here. It's 1.7 rather, close to 1. What is it? 1.6871, say 1.732. That's what I found. Okay. Then now I'm here. I'm right here. And I have made that real. So now what I have for the middle of the line, and I have, by doing that, I will be able to define D3, you can imagine, all right? But I will do it at the end. Or maybe I can do this right now. Why not doing this, find D3? How do I find D3? All right, from here, before I move. I don't want to come back and do this. I'll do it right now. I connect, if this is point, if I connect this point, the red one, with the center, practically this, and I extend it until here. All right, so, and I will read what it says here. Oops, not. Okay, and that says, I'm gonna read it right now. There, it says 0.1024, say this is 0.104 lambda from there. And then I'm extending this, which is this line there, and I'm reading this point here, which is 0.25. And the distance between these 2 points, which is, I will do it like that. The distance between these two is D3. This is D3. And D3 is 0.25 lambda minus 0.104 lambda. And that is 641 lambda. So I found that D3 is 0.146 lambda to be able to do what I'm suggesting. Okay, so now I'm at this point. And at that point, what I found is that my ZL excuse me, y input at CC prime is 1.72. So now where I am here at CC prime. To go from CC prime to BB prime and have an input impedance which is equal with respect to Z naught to 1, then I will have to find D2 and Z1. So here is how I'm going to take this part just to for your convenience, even if for me I will not do it separately, but I will do it now. I'll say copy. We copy this part here. Paste. Okay. So what do I have here and on this end as a Z? Z here, which is input at CC prime. If I denormalize it, becomes the normalized times the characteristic impedance I used to normalize it. And the characteristic impedance I used was Z naught. So it was 50 ohms. So if the denormalized value of this input impedance is 1.72, I think 1.72 times 50. It's 1.72 times 50, and that is in ohms. So my Z input at CC prime becomes how much is that? 65. No, is it 65? Let me see, make sure I don't make any mistakes. 72 times 50, 86, not 65. 1.72 times 50, 86 ohms. Okay. And now I want to select Z1 and D2. So okay, say the question here is find Z1, comma, D2, so that the input impedance here, Z then, if this is C prime, and this is B prime, we want Z input at B prime to be equal to 50 ohms. Because if it becomes 50 ohms, then I will be here at this end of the line with a 50 ohm load. And the line is 50 ohms characteristic impedance. So practically I have a perfect match right there. How do I do the perfect match? I remember the quarter wavelength transformer. So quarter wavelength, as we call it, transformer. What does that mean? That's very important. You need to remember it. Quarter wavelength transformer is this section of the line when D2 is a quarter of a wavelength. And in that case, if this is a quarter of a wavelength and Z1 is the square root between the input, which is here, this is one I'm going to create at the input of this Z input at BB prime times the load I have at the end of the line, which is this one. So is the product of these two inside the square root. All right, so there is a relationship that connects this one with this one, the input and the load. And that is the relationship in the quarter wavelength transformer. And therefore, from these two, I can find Z1 to be the square root of 50 times 86, which is, let me find it now, 86 times 50 square root 65.57. So say 65.5. 65.5 ohms. So I found my Z1, and now I claim that I have solved the problem. I have solved the problem because I have found D3, and D3 from here is 0.146 lambda. And so let me write here what I have found. All right, I found, therefore, after the solution, I found after the solution the following. D2 is what did I say? 0.146 lambda. 0.146 lambda. I found D3. I found D2 to be a quarter of a wavelength, and I found Z1 to be 65.5, and I solved the problem. And now with this, I have a zero reflection here. So my reflection coefficient at that point becomes 0. So this becomes 0. And that means that I have a perfect match at BB prime. Did you see how I solved the problem? So a big part of the solution, you need to remember, is to write what the problem is, to draw it, even as I said multiple times, and I will say it again. I will repeat it again. You have to draw this yourself. Even if I have it in a great detail, you have to draw it. Because this way, and make sure you have not left off anything, because a lot of times you are doing the wrong solution because something is missing from your thinking. So by drawing it, then everything is recorded. Then you write what I gave you, always. And then you write what you need to find. All right? And then you outline how you're going to solve it. And then you do it. So practically the solution is this, what you see here, that's the solution of your problem. And an equal amount is how you are going to prepare the problem for the solution. And that's how we do design. That's how I want you to think on how you're going to solve problems. Whatever problems they are. It might be these problems, it might be a software development, a code development, it could be something else that you wish to do as a career. But in all of your courses, that's how you have to approach the solution. You write down your problem yourselves, even if it's given to you. You write down what people have given you, everything. Make sure you don't miss anything. You write down what you are supposed to find. And then you write down how you think you're going to solve it. If you don't know how to solve it, well, if you don't know how to put this outline, then let me tell you, don't waste your time in trying to find any solution. Spend your time, even if you were to finish, I'm telling you something right now so you know. If your solution were to finish here, if that's how far you could go in the final, I can tell you I will give you at least 70% of the solution without anything else. But if you start here and you start doing stuff without any reason, I don't even know how you're thinking, you're not going to get more than like 30 or 40%. And I'm telling you, if you don't know how to do this, then I can bet you anything you are not gonna solve the problem. So at least try to spend your time developing that. And the chances then of moving quickly to do this, you can do this solution in 5 minutes, even 10 minutes. 10 minutes, let's assume. And in fact, you could even do this by hand and show me how you would get, and that you would give you close to 100%. Because my goal here is not to see the final number. I want to see how you solve the problem. And if you make a mistake early in the problem, then the chances are zero that you're going to come out with anything meaningful, especially if you make a fundamental mistake here because of misunderstanding of the questions or the problem itself. Okay, so that is, oops. Any questions on this? This is very similar to your homework, I believe.
Yes, Dr. Katahi, I was wondering if we could discuss the VSWR along the line.
Yes.
So
okay, let's find it. How about that? Do you gonna find it?
Well, I was more asking like how it changed like from like transmission line to transmission line. Like
okay,
for
so here's what happens. There is one VSWR here, a different VSWR here.
Yeah, so I was like asking like, for example, like even though the VSWR at AA prime to BB prime is 1, it can still be like a different value of 1 between BB prime, CC prime, and
yes.
CC prime, BB prime.
Yes.
And then also because like it's
and
a
what
lossless.
what does that really mean? Yes, go ahead. Yes.
Oh, I was just gonna say because it's a lossless line, because the points between BB prime and DD prime are all lossless and there are no like resistive elements, the power is still completely transferred to YFL regardless.
Yes. And you know why? Because what does that mean? The way I'm thinking about it is when your wave comes here, when your wave comes, it's going to see, forget about the wave seeing anything, like time t equals 0 plus. Then it's going to see a reflection here. Then the wave is going to come here, it's going to see another reflection. Then the wave is going to come here, see another reflection. But as those reflections come up, then eventually they all cancel out between A prime and BB prime. All right. However, there is a linking in between. So for example, what it means is the waves are bouncing back and forth in between BB prime, CC prime, and CC prime, DD prime. But at the end, so they're bouncing back and forth here. But at the end, they all contribute and they come there, the power. So yes, there is a reflection at the points CC prime, DD prime, but as the waves reflect, they all come with a phase, all right, because their phase changes. So eventually they all sum up to give give 0 here, reflection, 0 reflection here. All right. So you will have reflection coefficients at BB prime, CC prime, and another reflection, so different VSWRs at CC prime, DD prime, but the final result at AA prime, BB prime is going to be the reflection to be 0. So okay, a VSWR of 1.
That makes sense.
Yeah. Did everybody follow the discussion? There. My advice for those of you who have interest, try to find another solution, another possible solution to the problem. As we said, in every design, there are multiple solutions to the problem. Okay? So, try to do that, to see how else it's going to come out, because as I said, there are multiples, not just one. Here, I found the one that would be most convenient for me, practically. Okay? So I will upload that. We'll have more problem solving today. So try to come up, to show up. And then we are going, so because this is the week we're going to do all of transmission lines. We're not going to really solve anymore anything new in transmission lines. That's all we are going to do. And I think we've done a lot already in transmission lines for this class. Any other questions?
I have a question about the admittance.
About what?
Admittance.
Admittance, yes.
Yeah. The so when I was like looking online for Smith chart diagrams, I saw that like some of them have the admittance circles.
Oh no, I don't use them though. You know what? They are so confusing. They have been even confusing to me. So my advice is stick with simplicity.
So
we
can like,
yes.
So we can just like draw the diagonal line like through the center, through the center to find the corresponding impedance from admittance. Okay.
That's the easiest, because I have to tell you, if there are so many circles, first of all, that it's very easy to read the wrong one. That's the problem. That's why I don't go. You have to be really experienced to go into a Smith chart with multiple circles, and you cannot believe how many circles they can put on that. But I'm saying not now. Stick with the fundamentals in the Smith chart. That's very important. So if you want to go from impedance to admittance, go through the diagonal. Don't try to be on one Smith chart with multiple lines. The probability of reading the wrong number is so high that I cannot tell you. I mean, and you need to work with them every day of your life to be able to avoid that. So stick with the simple ones. Okay?
Got it. Thank you.
Sure. Any other questions? Okay.
Yeah, I had one about the problem we just did. Why did you choose the input at CC prime to be real?
Because then I can use the quarter wavelength transformer, because it has to be real for this to work. A quarter wavelength transformer, these two, cannot work unless the load is real. See?
Okay.
Did you get that?
Yeah. Okay, yeah. I was just thinking that there are like I guess other ways that you could solve this. Okay.
Yes, there are. Of course there are. Now, before you guys go, I need to tell you, and I will send a note. In my society, which is the Microwave Theory and Techniques, is the high frequency society that does these kinds of circuits. They have a program for undergraduate students who want to participate in their conference. And if you apply, it's a very simple application, and I can send it to you. Then they have a program for undergrads who want to understand more about the professional society. It's like very heavily industry based. And so I'll send it to you, because they will give you scholarship like money to go and either do it in person, because it's face-to-face and online. This year it is in June. So if you are interested, let me know. Send me a note and I will send you the application. I had many students who went to those conferences. I did not know they were going to have it this year, but it's very useful because you're going to see a lot of interesting things there. So if you are interested, let me know. Okay, so thank you. I'll send a note to everyone. I'll talk to you later.
Oh, wait, Professor, I had one more question.
Yes.
Did you finish the problem, the design problem from last lecture?
Yes. Did I know?
I'm sorry?
I think I did. I also placed it as an example because I cleaned it up. Let
Oh,
me,
okay.
let me see. Previous lecture. That was the 19th, wasn't it? This
Yeah.
one, isn't it?
Yeah, that one.
Yes. We measured, did I measure it? Did we, what did I not do? DS and Z prime. And I said we were, let me see. I think we did it. We solved it, see? The whole thing. Yeah, that is the one where I finished it. It's on your, it's on Canvas.
Is that the same problem?
It's 9 o'clock.
Let me see. Oh no, what did I do? They are two different. No. Okay, let me see what I have. I need to go, I remember I did a number of things. Definitions. Let me go, I'll let you know. Let me go and see on Canvas what I did. I remember I put two different things. Okay, I will check it out and I will send you a note, Eduardo, or everybody else. Okay, let me check it out. All right, talk to you later.